All right, all yours.
Okay, so my name is Louth. I'm originally from Ireland, and I lived in Holland now for over 10 years, so my accent will be a bit mixed. When we go to the pub later, we'll probably turn back to Irish. More drink, I'll get more Irish. If you come to this session, or this talk, to learn which data structure you should use to make something go fast, then you're going to be disappointed. Because that's not what I'm not going to discuss about how to tune systems. I'm going to focus really on the trend in terms of performance and where the responsibility of managing the performance of an application is today. For a long time, we've relied on the JVM and improvements both in hardware and as well as the JVM, the dynamic hotspot compiler, to improve our applications. Of course, we always tune ourselves, but we've had an easy ride where we gained 10 or 20% performance improvement with each release. What we expect is that that's going to change now. That more of the optimizations that the hotspot has done now has come to a ceiling, and really the responsibility is going to move up the application stack. Now, who is going to be responsible for that? We're not really sure, but it's going to be a layer between the JVM and the application itself, and it's going to be about how can I manage, how can I adapt. The JVM itself is a very adaptive system, and those techniques are probably going to have to move up into a higher level and be more adaptive in task management and scheduling. So what we're going to see is that the performance, the optimization of systems, especially systems that have been already quite tuned, the focus will be there on people bringing in expertise on how to apply system dynamics, how to manage the system in terms of its workload. So up to now we've kind of tried to get code to go, to be faster, to reduce the amount of code that's executed, the consumption. But really the future will be more about how can I schedule this work, how can I partition it, how can I schedule the execution, and how can I manage the resources in that layer. And up to now, if you look at your most Java applications today, they just run, and your request comes in, like a typical web app, the request will come in, and the code will execute it. There's no thought to whether I can execute this at this moment. Am I currently suffering because I'm doing lots of GC cycles? Applications today have, even though they're intelligent, maybe they might appear intelligent to the user in terms of what service they offer. They're pretty dumb applications. If the request comes in and it fails, that request may be because the database is currently down, and the next request comes back in, what will happen? The application will execute the same code. It always executes the same behavior. It never adapts to both the environment and to its own performance. It's not aware of itself. And so we believe that the future will be on terms of optimization and management of these systems will be on software that's able to be aware of itself via observation. And not just observation as in a dashboard, that someone's looking at a dashboard, but the observation is happening inside the application itself. And it uses that information to adapt its behavior. And that could be changing algorithms, changing data structures, or also scheduling like QoS, prioritization, and also throttling the traffic, throttling the costs. And so when we do that, a lot of that at the network, in the internet, and those kind of techniques are probably going to move up into the JVM itself. Because this is the only way that we can manage systems like this. So that's kind of the big picture. So the trends that are bringing this to a head are that, of course, we're moving to cloud computing, where it's simply unlimited resources. Well, it's unlimited in that it's possible to get there. Of course, there's always a cost in terms of financial costs, and then each additional unit will have some sort of cost in terms of management of overhead, operational overhead, or the value that you can get from it, the efficiency. But cloud computing is offered this more, unlimited capacity there, at least dynamic elasticity. And then, of course, we have the sea of change. Sea of change is that everybody is expected to change applications quite quickly. I remember someone just recently on Twitter said that he deploys his application 50 times a day. That's like every 15 minutes. Now, if it's being applied every 15 minutes, how does operations handle a problem? Like, which version of the code is it? 15 minutes ago. By the time 60 minutes have already lapsed and someone's already applied a new version of the code. They might say, well, it might have healed itself already. So that's where we have this, like, you know, the sea change where it's much more dynamic. Then, of course, we're moving to more platforms where we have the runtime, but we're looking for more platforms to kind of take away a lot of the overhead or the complexity in managing these systems, especially in the cloud context. And that's typical, like in a PaaS environment. We're going to be looking for that. And more probably grid environments. I don't think PaaS that we have today, the version 1 that we have today, is really suitable for this. But we're probably going to move more to a grid, at least in a much more abstract execution environment. And then, of course, we have parallel processing, where along with functional, which is tagging along with that. And of course, we have a large number of cores coming along, and we have to do something with them. So these are the changes in the industry. Now, to come down to performance optimization, I just want to give you a little quick history of how we got to in terms of application performance management or application performance monitoring. And so when we started, a lot of the monitoring tools that we've had that we use today started with the client server, or at least, it was mainly, of course, in the mainframe part, but if we just look at the client server, we started with monitoring. A typical monitoring is metric monitoring. And then, of course, metric monitoring, people had lots of metrics, they had thousands of metrics, maybe hundreds of thousands of metrics, but people really still didn't be able to solve or understand applications. So the industry then came along and said, I've got a solution, like it always does when it sees it creates a problem and says, I've got another solution for all of those million metrics that you have. I'll give you diagnostics. And diagnostics is basically what is happening now, what is the typical dumps. Like if you think of diagnostics, what's the standard diagnostics for Java? Stacked up. Everybody does a thread stacked up. So these are kind of, getting the state, what's happening now, and what's the state of the JVM itself. So diagnostics were meant to a solution where we were able to collect this data, capture more state data, and hopefully solve the problems. But of course, it didn't really solve the problems, and we had much more distributed computing then come along. And then people said, okay, well, I've got diagnostics, that's not really happening because I've got hundreds or thousands of dump files in a directory, so what do I do? So the industry answered that question by saying, we'll give you analytics. And analytics will analyze the diagnostics, because we can't analyze 1,000 files, and look at all of those files and come up with the root cause. So then we came to more analytics. So along with that, then we're starting to move to more utility computing and grid computing, where when we look at grid computing, it's about taking a job and spreading it and pushing the execution out onto nodes. And of course, in that, we're looking to optimize its execution of where to place it, where is there available resources that will execute the job within a reasonable time. So grid computing forces us to start looking at optimization in terms of optimizing the scheduling, the placement of it. Of course, now we're moving to utility computing, which is more this, every time I make a call, someone's probably going to charge me, I'm consuming resources, and I don't have to really pay for them. I don't really have to pay for them, I don't have to actually go get them. I don't have to order a PO, get a PO. Of course, the problem with that is, the complexity is that we have a very large number of moving parts to the system now. Because suddenly, we have capacity that can go up and down. We can suddenly go from 100 to like maybe 10 to 100 to 1,000 JVMs. And so really, how do you manage something like that? And of course, because the capacity is changing, the software has to change. Now, we haven't really probably changed software today, but we believe that to really take advantage of this elasticity, we need software to be adaptable to this new environment. So if software says, I've got new resources, I should utilize them. Or the resources have been constrained, I have to operate in a different mode. And most biological systems will operate in that. And they look at the environment. So to deal with those, we feel there's two solutions to that. Is we need the ability to meet the systems. We need to be able to say, what am I consuming? And which code, and which code call which code can make this consumption. So we need to be able to track consumption, especially in the utility environment, because that's what we do with billing.
So doesn't the JVM do lots of this stuff, like it'll optimize code?
The JVM is an adaptive system, so when it looks at your code, it's looking at how quickly it executes or the frequency of execution, and then it uses that information then to optimize it. And of course then to determine whether it should go to further optimization. And of course then it looks at the code and then tries to optimize it and then move it more to native code. So the JVM is already adapting. That adaptation is already happening there. But the adaptation now is going to have to move to a higher level. So all biological systems, layers and layers, and we're going to see more of that happening in the application stack rather than the JVM. At the moment, the JVM just says I'll optimize the bytecode. But if you take your application, you're having many users that are consuming it. Some of those users might be, let's say, VIP customers, and you want them to get maybe preferential treatment. Now, the JVM doesn't see the difference between that's just bytecode. It doesn't see that there's a user that probably is doing a service which needs, guaranteed kind of response time, or you want to give prioritization to a particular workload or a particular user group. So that can't be seen by the JVM itself, because it's more contextual, and that context is in the application. So the JVM can't look up and say, I understand applications.
Maybe another example would be like graceful degradation. So if you work on this server goes too high, like you switch your site into read-only mode. Would that be another example?
Yeah. It's also like GC garbage collection. I mean, the garbage, the JVM itself today will schedule the garbage collection. But of course, what you should be doing is it's determining what's your limits. There's no point in running in and letting all the threads, go in there and create all the allocation. And then for the GC to say, hey, I scheduled myself and I'm going to go along and clear it up. Really, it'd be much more efficient if you throttle the system itself to stop the GC. Because the problem with GC is that we get to limits, and those limits are very dangerous because we crash the JVM. And we don't want that. Now, so what we want to do is, of course, the application, the JVM says, I will just clear objects. But really, who is generating the objects? What workload is creating that? And that's in the application. So it would be better for the application to decide, I should throttle these requests rather than the JVM just keep cycling around saying, I'll keep cleaning up as you keep creating a mess. So there has to be some more coordination between them. So we want GC to happen, but we want to throttle the allocation rate. So we rely on GC, but we can't push it all the way through because it creates much more of a pile. And the overhead is much higher there. It's a bit like it's a bit like developers. If you ask the developers how many threads you want in the JVM, he says 1,000. They don't understand that there's a context switch to all of it. They don't understand the overhead that's involved in that. So the application itself has to take more responsibility for that. Now today, like if you think about thread pools, what sizing? Who does that? Does the JVM do sizing of the thread pool? No, because it doesn't know who's consuming the thread pool, and it can't say that it's always this type of request that does it. Because it doesn't understand the request. It says there's a bit of code, but it doesn't look at tracing. So if we were to say thread pools, the JVM sees bytecode, but it doesn't say there's a particular instance and it's always consumed by these services. And when it's these services, then the thread pool size should be this. And that's really the application itself. So then we need the software to be this brings on to self-regulation. The software has to be self-regulated. Software needs to be able to manage itself, to kind of to prioritize, to control, to police the application itself. And these are, of course, all general principles that not just applicable to Java, but to many applications, many types of application runtimes itself. And of course, to help with that, we need a feedback and control system. Now, the reason we have metering is because you can't control a system unless you understand the observations that you make. So the first part about self-awareness is to know what's happening in your application. So when you go for a jog and you start sweating, you're aware of your sweating, you're aware of your heartbeat. What do you do when you start suffering or you start sweating profusely, or like your heartbeat starts racing? What do? You generally stop, don't you? Well, does anybody know any Java application today that stops? It says, I'm a bit busy now. I think I'm just going to hit the limit and I'm going to slow down now. No application today. It says I will keep going until I hit the wall. And that is either the GC wall or until I get myself into a particular state. So we need the software to understand, to be aware of, probe its limits, be able to pull back, take that observation and pull back and say, okay, when I did that, that wasn't good. So I'm not going to do that again. Or at least I'm not going to do that again for the next few minutes. And so that's what we need. But of course, to do that in these observations.
So what kind of level of feature are you talking about, like method execution times or more high level, like the time it takes to serve a request?
Well,
Or
yeah, well, it could be. Well, okay, yeah. So that's, yeah, well, we'll get onto that. So the part is that we need measurement. The problem is that if we measure everything, we'll be overloaded with data. So it's like if you look at yourself today, you know particular metrics which will be useful for you to self-regulate. So your temperature, your heartbeat rate, we know those particular metrics. And they're applicable to pretty much all of us. Unfortunately, with Java applications, or any applications, they're all different because everybody designs them. Every application is pretty unique, so we don't have a single reference, biological system that says this is what all people, we have all humans look like this. Can all applications look like that? No. So we want to be able to measure, but the system has to learn which particular metrics or measurements it needs to keep monitoring.
Yeah, so you're going down this, there are kind of like two big kind of paths that are in this, what's going on with very complex dynamic systems.
Yes.
One path is this area where you want to be able to bring in, more visibility and new functions at the system level to improve application performance. But I'm going to go back to one that you mentioned was, with these systems that are rapidly evolving and they're a very complex state, there's a problem about reproducibility. Like so you talk about one of these people say, well, we just give up. We don't even, as long as the systems, our overall metrics are good, we're improving their overall state, we don't spend a lot of time trying to go back and diagnosing particular failures. But that's another track, right? Which is reproducibility in large systems. And where do you think?
Well, I believe we can. This is the issue: is we have a significant rate of change. So it's very, very hard. We're going to have a change in terms of code. We're going to have a change in terms of capacity of consumption, and we're going to have a change in terms of workload. We're not in control of the workload. Users are in control of it. They push it to us. And of course, unless we put some mechanism in that controls the workload, at least the rate. So today we really haven't got much control, but we want to have this, I understand application. At least I have a model of what this application does. But I'm saying is that if it's truly a complex adaptive system, we can't manage it that way. So the system has to first, in every instantiation of this application, it has to undergo a learning phase. And if you look at the JVM today is able to run all of your applications, and they're all different, but yet able to optimize them. And what does it do? Every time it runs, it does the same procedure again. It tries to learn what should be compiled. What is the hotspots in the system. And of course, those hotspots are never the same. So the system's very dynamic today, so we can run multiple benchmarks, even for the same tests. And we still get quite different numbers. Not significantly different, but there will be difference. So our view is that we have to accept that there is this kind of, that we will not be able to understand the system, but we have to put mechanisms in place to allow the system to stabilize, to be able to contract, to expand and contract. So as engineers, we'll be focused more on the mechanics of control and stability and resilience, but not on understanding what the application is. What we need to do is put controllers in place that observe, and then we'll get onto this. Okay, so the problem is, the first problem to all of this is I collect data, what part of the data should I collect? This is the first issue. For self-awareness, if we're taking my system myself now, should I put a probe in every single vein in my body? That would be like what application software is today. Should I put instrumentation at every single site or code, call site, method in the application itself? So how do we, of course we have main arteries, we have systems in place where we're able to understand what the functions of all of this, but applications are not. So the first part is we need to measure, and the measurement in some way has to use that data to start adapting the measurement itself. Because we can't go to self-awareness if we have everything in place because we can't figure out what is the proper signals that we should be watched out for. So we start off with the first problem is data. Now I'm connecting this to the application. So what we have today is there's two aspects to data, measurement data. Because we first of all, for self-awareness, we have to aware of ourselves and then using that awareness to adapt ourselves. So if you look at applications today, we have two types of data in terms of, we have a temporal aspect, and then we have a locality aspect, or spatial. So the first part is we take the local and remote. A lot of data, metric data, or monitoring data, or behavioral data, exceptions, or any observation is generally sent to a log file. Most systems today, people just write to a log file. And I view that as remote. And it might also be like it's published in JMX and some management tool pulls it over. So today we have a lot of that, and it's remote data. Now, local data is something that's inside the application. The data is maintained in the application. And this could be typically like an ending, a metric. Measurements that are inside the application, like the JVM today will tell you how much our heap size is, how much it's using. So this is the type of metric measures we have today. Unfortunately, we don't have behavior. We have kind of like, what is it now? A number, or a counter, or a gauge. But we don't understand, what did I just do? So what we need to understand then is behavioral. And when we look at behavior, at least in self-learning, we need to understand what did we previously do, what was the past, what are we currently doing, and using that context, what do I predict I'm going to do next? So let's say I want to do a request. If I've observed this request and I've figured out what I do with this, the main part of this request processing, and I know where I currently am in an instance of that request, then I can predict what I'm going to probably do next. So let's say a request comes in and I always go to the database and I go to JMS. Now, at this moment, I'm doing a request of that type and I've just done the database. So what can I predict I'm going to do next? More than likely, the messaging part. I can probably already predict how much time I've still left to do in the request. So, by understanding what we previously did, by keeping the profile of that behavior, and then understanding where we are currently doing something, and then using that to predict what's going to happen next. So that's what we want data to be focused on. Now, we want that to be local. Because how many applications do you have today that read a log file to diagnose themselves? An application writes to a log file because he wants to forget it. He doesn't actually consume the data. It says, I'm doing GC. Well, I don't know because it's in the log file. No, the application itself hasn't got the data. Now, there's a reason. Now, there's two parts to that. Is that what we have is a big information model, but what we want really is the management model. What part of all of that information that we have on the JVM is really useful for management. And management in terms of how can I control, how can I use that to predict the system itself. So the goal is to get down to the management model. Now, because of time, there's basically what we have today is for most systems we have metrics. Metrics is the most typical approach to measurement today, where someone takes a metric or has many metrics from different types of components, and these are sampled every maybe a second or 10 seconds or a minute from a monitoring tool, and then they're at the process level, so there's a counter that says how many transactions I did. And then, of course, when there's a problem, someone comes along and does correlation. So it says, I got a problem with my GC, GC went high, and it looks at the other metrics and finds out which metric is spiking at the same time. Typically, it's that visual correlation. And, of course, you can do statistical correlation, but it's still correlation-based. And, of course, when something goes wrong or when there's a high CPU on a management dashboard, someone apportions blame. And they'll look at various metrics or various transactions. Let's say there's two types of transactions you're tracking, and it will apportion maybe some of that CPU to them. It doesn't know for sure which one caused it, and this is the problem. The problem with metrics is it doesn't tell you cost. It doesn't give you the information of when the CPU goes up. We go into customers and they say, here's the CPU chart, fix that problem. And I'm like, well, that could be good. High CPU could be good problem to have. Or how do I know who caused the CPU? We need to know about consumption. So metering is about is that when there's a resource, it's consumed, and we track it by in terms of the event. So when I go to the CPU, I track it. And typically, the accounting function today for that is thread CPU time. Most operating systems will give you the CPU per thread. They give the accounting on that. So it's on a thread basis. This is important, is that when a thread does something, he can say, what did I just consume? He can say, I consumed this amount of CPU. I did this amount of I/O. So when you call to Amazon, what does Amazon come back with you? Well, if it came back with header information that says, how many bytes did you write, or did you write into the system, how many bytes did you read out, how much CPU was consumed in that, depending on that billing, and how much they're going to charge you for that call, especially if you have a to-do task. So it's based on the request basis of the thread basis, and it's direct. We know it's direct here. So that's basically a metering system. It's based on the thread of the worker consumes it. So if I go somewhere and I do something, the consumption goes to me, and of course if it goes to the thread, I'll get to you now. If it goes to the thread, it goes all the way up the call stack. And all the way up the call stack means that every activity or every code on that stack has an assignment of that cost. Of course, one is going to be direct, and the rest of it will be indirect.
So we're doing asynchronous request processing the tracking by thread doesn't quite.
Yeah, well, of course, yeah, but of course, like when you, let's say we're two threads, and I'm given a job to do, and I say, go do that job for me. So my manager comes along and says, I want you to do this job, and what I'm going to do is outsource it to you. So I get you to do the job, and then you come back with the job and give it back to him. Now, of course, you'll send me an invoice, and then I'll add my commission on, or my profit, and I'll give it to the manager. So there's still individual metering at the thread level, but there is a transfer function. So you still do metering that when you do your time, you'll send to me, well, you might get 8 hours on that job that you gave me, and I'm charging 8 hours by $100. I don't know the rate is here. And so you're going to send me a bill for the rate, and then I'm going to see how long I was working. Well, I'm going to take your time, and then I'm going to the time I need to coordinate you, and then I'm going to give it to my manager. So you can still have that time. There just has to be a transfer function. But the thread itself, like if you were saying when you do you might have a different rate depending on what you did. So let's say when you're coding, you have a different rate. When you're driving, let's say you drive to the customer. So there's a driving time and then there's a coding time, and they give you different rates, but you'll still be assigned the cost, yeah, and the cost will be transferred to me. So that still is handled by that. We have to be able to, because we need to understand what's driving your work, what drives you. So typically an activity-based system is there's an activity that causes consumption. And what we want is like a method calls another method. So that's the activity. So an activity is a very general concept, but it could be a request, but typically of course one method calls another method. And that represents behavior. And when behavior happens, or the occurrence of the behavior, we want a consumption, whatever it is. Now a typical consumption would be clock time. Time passes by, so that's a consumption of walk time, but it could also be CPU time. And generally, we're counting something. A meter is about something that grows continuously, and we take it. We say when we do a job, we read the meter, and then when we finish the job, we read the meter again, and the delta is what we consume. So that's basically the metering. Now, the big problem with all of this is that if with the instrument, the typical way to do things today is instrument, measure, and collect. Instrumentation is like you writing system nanotime. Start equals system nanotime. End equals system nanotime. And then you're taking the delta, which is what time just passed by, and then that's the measurement. Say I measured the clock time twice, I took the delta, and then what's the collection? Typically to a log file. The problem with all of that is that if we put that in every part of the code, the system would slow down because there's a significant overhead to that. So the first part of all of this is that the system needs this to be adaptive. So to create truly adaptive systems have to be built on adaptive systems themselves. So we already have a JVM that's very adaptive. So the first part is that we need the measurement system to be adaptive. So instrument code determine what to measure, and then narrow down what is measured, then narrow down what is collected. What is interesting? So that's, for example, we instrument. So let's say instrumentation is the big set. After a period of time, we look at the measurement that we're making, and we say we're not going to measure this anymore because it's too cheap. And then, of course, every time we take a measurement, we look at the delta and we say, should I collect this? And why would you not? You probably won't collect data or log it unless it exceeds some SLA or something like that. So what we need to, first of all, is to make a system to break that down to that whatever is instrumented might not be measured and might not be collected, depending on the system itself. Okay, so just to show this in action, first of all. Okay, so if we take this as a simple application here, I've got a call here, and this is done. It's going to do a run, and I'm going to do a run count, which is probably 10,000 there. Now, if I run that just with normal, this is what hotspot does. Now we know hotspot's going to see that this is an empty method, and then it's going to inline loop. It's going to say empty is empty loop, and then basically this becomes 0. So if we run that, and I'm printing out the nano time there, at least the time per method call. If I run that. This is what we get, yeah? We get 0 cost, nano time. Now, of course, if someone says, I want you to measure this because it's a bottleneck, and to be honest, it would be a bottleneck. If you did sampling, that would come in all the time on top. So someone says, I want you to time it. So you do that, and you have to do this at least the minimum, and then of course you have to collect it and take the delta. But let's say we put that in the system there. We start to slow the system down. Now, of course, you might say, oh, it's only 72 nanoseconds. But when we put that in a big system where everybody's calling everybody, that overhead quickly multiplies. So clearly, you need the mechanism. Now, if you were to put that in your code today, it's going to be there forever. You know, if you put in nano time and then nano time delta and log it will always be there. Rarely is it going to change. So we initially need a system that adaptive, is able to measure. Now, I don't hate to do kind of a sales pitch on our product. I'm mainly the vision. But I'm going to show you our system is an example of what adaptation looks like. So we put adaptation into our measurement system itself. So I'm going to now run this with our technology that measures code. Now, initially, I'm going to run it without our strategy. So our strategy is basically our hotspot strategy that adapts, looks at the measurements, and turns off instrumentation. So if I run that with just a basic, which is no intelligence, the overhead will be 190 something, because we're measuring and we have to collect it somewhere. Now, if I put on a strategy system, so if I do that, we'll see if I put out an XML file. We know we have a UI, but I made just do an XML file. You can see that it's measuring the calls. There's a meter clock time and the number of times executed it in the total. Now, what we really would like the system to do is to eliminate that measurement, to not measure it. So if I get rid of this comment, and run it again, it goes to 0. Now you're probably saying, oh, Will has run away with a magic flag that doesn't do any measurement. But if I show you here, if I look at the XML file, you'll see that this is the probe, the method that was instrumented, and we measured 1,000. We looked at the total clock time, and we thought it was too cheap, and we disabled the instrumentation. And the time went back, the overhead went back down to 0. But probably the first one, if we look at the first one, was a bit higher, because of the cost of 0.1, but it went down to 0. So the system learned, the measurement system is now adapted. Now the reason for this is that we want the system to learn what should be measured. I mean, of course, the hotspot would be pretty good if it did it, but it doesn't do it because we might be not just measuring clock time, we might be measuring other consumption that's related to that method itself.
Let's just go out and say, you had a probe in there, measuring something or other,
Yeah.
and the first measurement made it felt.
Well, 1,000, weights like 1,000, like hotspots. And it says, on 1,000, I looked at how much I've measured up to now. I said, wow, my measurement overhead is much higher than this method.
This turns itself off.
Turns itself off. So very like the hotspot itself.
If you look like a sleep in there, it will turn itself on.
No. Well, yeah, well, of course, if I put something in, yeah, it'll stay, yeah. So if I, yeah, I understand what you mean. So if I slow it down,
to stay alive,
yeah, if I did it lots, well, of course, it's going to take a bit longer, but I just have to, that's 1 second, is it? Just to make it a bit, we won't wait all day here. So, now I'll end it shortly, but you'll see that it will move past the 1000. Just look at the XML of the loop is. If you look at the XML file, you'll see that we're up to 8859. So the system hasn't disabled this probe because it's slow now. Now, so and that's the problem with instrumentation, is that you instrument today, you're making the decision. The system should make the decision, not you. And so this is an adaptive measurement system. So we view that, okay, we have the JVM being adaptive in terms of optimization. We have an adaptive measurement system, which can get rid of all of the data that we need to collect. And the next stage is actions.
But don't you have rules or something somewhere kind of?
Oh yeah, which is like a system. Yeah, every adaptive system has some kind of parameters to its model and how we use it. But of course you can tune them. You have thresholds and all, but I don't want to get too much into the product. But of course everything is an adaptive system and it has kind of knobs.
So I mean, it's not a self-adaptive system. It's an
Well, it is a self-adaptive, but every adaptive system has to operate in some kind of boundaries. Yeah.
The slightly more tricky question would be if it got slow later on, would it re-instrument that method?
No, because it's eliminated the
Once it's gone for good?
Yes. Yeah, but it's very like, well, of course, this is only meant to eliminate the noise, the stuff that we wouldn't want to. The other stuff should be always borderline. You wouldn't put this close to your threshold of what a hotspot is. You'd put this to eliminate all getters and setters.
Right, but wouldn't the problem be if it's really dynamic? I mean, that call mostly takes no time, but occasionally it blocks and it takes 5 seconds.
Oh yeah,
with instrumentation, you won't know that that's what the problem is.
Yeah, but if any code that takes occasionally 5 seconds will never execute in a few nanoseconds the first time, or a few times.
Well, if you pass in I and you said if...
Oh yeah, if there was, yeah.
Well, I mean, and more realistically, you called, like sometimes I make this call and other times I don't. And the call is a database call and other times I don't need to make a call through it. So let's say I'm a cache.
Yeah.
I get a cache hit, I don't need to look up there or not. I mean, isn't there a risk that you would suddenly throw out the really important stuff?
I'm going to come on to that at the end if I can get the signals. That's called signals. I have a solution for that. But to be honest, the measurement, if it changes, there's always a guy above on the stack that's not adapting because he might not be the one that's just calling it. So there's a measurement. What happens is the cost gets assigned to the guy above.
Okay.
Well, that's kind of my question. Actually, any particular time value is not what you want to know. The criteria is actually how informative is the probe.
Yes.
That if it correlates, if either it's unchanging or correlated to another measurement, that would be the criterion to equal information.
Yeah, well this particular strategy at this stage is trying to say, I'm trying to improve the relevance of the data. The first part is the accuracy. Relevance we want, but we first need to eliminate measurements that will perturb the rest of the accuracy. Because there's no point of saying, I've got something now that's relevant, when apparently it's being perturbed by the measurement that's due. So the initial stage is to clean the data. And cleaning data means getting rid of all of these getters and setters, because that's the problem with Java. It has lots of getters and setters. Like if you look at the tree structure, a lot of the leaves on the call tree are simply doing nothing, or doing no matter, relatively cheap. So really what you want the system is to be able to find boundaries in the system. Figure out okay, we have all of this code, think of these as the circles, but figure out where the red dots are. It's like our artery system. Find out the main junctions. It's looking at a city traffic system. Figure out where bottlenecks happen. What are the main junctions? You don't want to measure every single lane, but you want to figure out, once the system's warmed up, is where should I be measuring my system? And that's what the measurement system should be. I've got about 50 adaptive strategies. But I just want to show us that we have an adaptive measurement. And that's what systems will be. You need that to eliminate the noise. So basically what our system does is starts measuring the whole world and has very little, the value here is small because of course the accuracy is, is questionable on it. And then what it does is it starts eliminating the instrumentation, and that improves the accuracy of the data and brings down bringing down the overhead. And of course, with that, we then start to collect a bit more information because we have a budget. And it's a bit like, we have budget. So when you make something cheaper, we always say, well, I'm going to use that money for something else. So the system then says, I'm going to start collecting a bit more data than I didn't do before because I just saved a bit of data here. And so that's what our system, and eventually our system will stabilize and it will be both, the value and the data is the same. What we collect is what's valuable to the application itself.
So when you say money, you mean the overhead that you're willing to allow?
Yes. We're going to get the budget on that. So, so when you look at the performance system, people always, we look back at the call that we just had there. The bottleneck in that system, where was it? Remember the piece of code that I just showed you? Where was the bottleneck? What was I doing all the time? Call. Now, where would you fix that problem? So if I was a manager and I came to you and I'd ask people this question in an interview. So, if you were asked by someone here, ignoring this, by the way, so you were asked to tune that, what would your solution be? How would you make that faster? I said to you, just make that faster. Just forget about the hospital. I mean, the hospital's helping you, but you can't do that anymore.
Coming out and include the call.
Coming at the call, yeah? Well, the problem is that run is calling it. So you can't comment at the call.
Better solution is just to reduce your run count a little bit.
Yes.
You don't want to have all the improvement in one code, so then later on you can sell the manager again.
Yes. Well, okay. Well, the fact is that to fix this code, we don't go to where the bottleneck is. We go slightly above it. So it's a bit like if you take a database. Every database is a bottleneck. We all know that. Every application today is an SQL problem. It's a shame. I'm ashamed of it, but unfortunately, we don't focus too much on SQL. We focus on trading systems. But most applications today have SQL problems. Now, how do we fix those SQL problems? Generally, people try not to execute the SQL. We're trying to optimize SQL from where it's been called. So, when we're looking at hotspot systems, the observation or where the bottleneck is, it's the observation slightly above it. So when we come back to your issue where we talked about this method might change over time, eventually the cost will move up to guys above it on the stack. And that's actually the location that's most appropriate to fix the problem. So developers always want the performance profiling tool to go to the line of code that's where the problem is, but it's not. That's where the problem is, but where you start fixing it is not there. Is always generally a few calls upwards, because you need to stop going down here. Of course, as one person said, delete code, because if you delete code, it's the fastest you can get. But unfortunately, someone's calling it, so they expect that there. So what you have to do is call it less. Don't go into that method, and if you look at that method, then you try to reduce its callers. So the hotspot, and of course, as soon as we get close to this measurement, and this is what happens with profiles, as soon as you get close to the measurement, you start to get pushed back because you start to measure that method, and then you start to slow down the system, and then the numbers all change. How many people have run a test and then they run it with a profile, and it's a completely different system. And then you still go into the manager, I figured out where the problem is. It's the database. So once the system has changed, we're looking at a different application itself, a different behavior. So we want the system to be quite close to that behavior itself. So one solution is to have a budget mechanism to say that, okay, I look at these methods as I execute, and this is where the hotspot can see it. The hotspot says, I just optimize methods, but there is a call tree in our applications, behavior. So the hotspot is all about taking a piece of code, a class, a method, and optimizing its behavior within that block. But what about when calls are flowing down? And we want to say stop measuring or stop going down there because you know, for the overhead. You know, we have a budget. I don't want you to measure as you continually go down there. So what we can do is to look at the methods and see how quickly execute. And then as we go down the path, like at the top level, like we have 100, and we say we'll give a budget of 5 microseconds. And let's say for every measurement it takes 1 microsecond. So then we take one away, we go down to the next one, we take one away, we go down to the next one. We look at his overhead is 50, which gives us, if we talk about, if we say the 2% or 4% overhead, we can calculate 2 microseconds, one for him and then one for one of his children. So we can control the budgeting of the measurement by simply for the system to be aware that as it's going down, what does this method typically execute? What's the average time? And look at that average time, calculate the budget, and go forward. And of course, every time we go further down, it refines the budget because sometimes the methods below it are like it. You know, the budget's in the parent. So to give you an example like that kind of runtime behavior, which a JVM can see, here's a piece of code that does S10, that calls all the way down to 1, yeah? And as it goes down, it calls left and right, and then of course it calls 9, and then 8, and 7, 6, 5, 4, 3, 2, 1. Okay. Now, if I run that, within the budget, I'm running without, I'm just going to run it now. It's measuring it at the moment. Now if I just take a snapshot here, I want the XML. Again. You see that the code, as it's calling here, I've got my 100, my 10, my 10, 1, 2, these are the numbers here. You'll see them, they're all measured here, yeah? So each one's being measured. Of course, I want to control the system itself. I want to say, okay, I'm going to give it a budget as I go down. So what we can do is give a budget, turn on the budget capability for the system to be dynamic, adaptive. And let's say we just give it a budget of 1% of overhead. This is where we control the tweaks. Remember we talked about. So I'm going to change the dynamics of the system by tweaking on what I'm willing to pay or willing to incur. So if I go to my budget now, it's disabled. The budget here, you'll see that it's gone. Each of them have been given 1,000 because I already gave 1%. Yeah, so it went down to 1,000, and the only guy that's running is this 10 here. He's still going on, and the reason is that 10 is up at the top. I gave 1%. So I only got the first one, because he looks at his average, calculates a 1% budget, and goes down. Now if I change the budget,
Can you go back to the XML? I'm not clear for that.
yeah, so what's happening here then is that the guys, we already know that every time 10 calls, he calls 9. But if you look at 9 is only measured 1,000 times. Well, 10 is measured 72,000 times. Now they're always at 1 to 1, but what's happened is the system says, I'm not measuring anymore because you haven't got a budget. The budget, it calculates a budget for 10, and that budget restricts the depth to 10, to that actual method. Now if I increase my budget by like up to 5, you'll see that now I'm measuring 10, 9, 8, 7, 6, and I stop it a little bit here. So the system, I'm controlling the measurement of the system by knots. By setting, the system is adaptive, it looks at what happens at that time, but I give it an overhead that I'm willing to accept. And this is very much like what we do to the JVM today, with hospital with memory settings and all.
So what does the 5% denote?
The 5% says it's like, I'll take the average cost, the average clock time for this method. I'll take 5% of that, and that's the budget I'll give for the measurement. And by default, the measurement says 1 microsecond for every measurement. By
That's
default,
the
it's
overhead you're willing to
yeah, you're willing the overhead.
So if you have a limited budget, why not do sampling instead of instrumentation?
Because we want to because sampling doesn't give us mins and max and counts. We want to understand the behavior of the system and also control. We can't control the system by just sampling. We'll get to why we have to do it. Because, okay, so I have to do a quick, I'm way too long now. Okay, so the problem, I already talked about this at the start, is that the issue we have at the moment in terms of all of this, and the reason why we came to the knobs, is that up to now we've always wanted to manage these systems and monitor them and control them. But really applications of the future will not be managed the typical way as someone looks at a dashboard and there's a big circle and it turns red. So what do you do today when operations see a red circle? What do they do? What's your standard operating procedure when you see red on some dashboard? Kill the JVM? Wait, go get a coffee and come back and wait for it, hopefully it's green. There's no control. Today, operations, the only thing they do is, should I kill it? When should I kill the JVM? That's the typical standard operation is wait, it's red for 5 minutes, kill. Other than that, has no other control. There's no other than they wait for something to happen differently.
It's not uncommon to do something like elastic feedstock. If you see like, oh, my servers are getting overloaded, I can spin up more.
Yeah, that's a way of adding capacity. Yeah, so you're introducing more capacity. Of course, you have to redirect it, but it doesn't mean that doesn't tell you whether you solve the problem because it might not be a workload issue. So, but yeah, in some ways it is a control. You need to redirect traffic, but generally it's not done that way because you don't understand whether it's the workload is issue because you don't know whether it is caused by workload coming in or is it simply the system is spinning. You know, the applications have gotten themselves into a mess. So, what all of this is the problem is that we've got a huge space that's growing. We're gone from 10 to 100 to 1,000 JVMs. And then, so we have to collect all of that data, and then the time resolution. The time resolution now has moved from minutes, people used to detect metrics, to seconds, people want metrics, and then to microseconds. People want real-time data. But we can't get real-time data as the size of the space is growing. Because I can't tell you what's happening in the system that has 1,000 JVMs. In a distributed system. So this is the problem. And we can't manage it in the dashboard because it can't get to the dashboard in time. And what is my reaction response time? What's my typical reaction time? Seconds? Minutes? Like, is it going to go green? So you can't even respond. And by the time you responded, the system could have changed. It could have reverted back to a stable state. So the problem is that we're involved in the loop. We have to exclude ourselves from the loop. So we can't look at these dashboards. This is a typical dashboard from Netflix. We can't look at these dashboards. They're not helping us. The way to help is to get the software to manage itself. Today, it'd be like, the way we manage systems is like for us to be, every time the JVM executes the code, to actually talk to us and say, should I optimize this video? That's what we're trying to do with our infrastructure today is what we would be like asking the hospital to every time it looks at the method to ask me whether I should tune it or not. And I'm meant to tune it in real time. Clearly, I can't operate that fast. So, I'm going to quickly go through some of this. So, the problem is we need to be able to get this awareness. But the reason we need awareness is we need, and this is the basis of it, we need to profile the stuff. Profile in terms of measurement, profile in terms of behavior, and then you use that profiling information to protect the system. Protect it is in what's coming in and to control that behavior. Say, okay, I know what's coming in and I can't take this workload. It's a bit like a restaurant. If you go into a restaurant, you might walk in and see an empty table, but they might say that you haven't got any space available because they can look at the kitchen and see that the kitchen is maybe taxed. It can't keep up with the current load in the restaurant itself. So they protect the system. And we have to get software to start protecting itself. Is to understand profile data, look at workload coming in, say, can I do this workload in time? So if when your manager comes to you, you already protect yourself, don't you? Because when he comes over and gives you a pile, what do you say? I can't do all of that. You better give it to someone else. So we do that today, but the software doesn't do that today. Policing it is typically just maybe like just some bad behavior, someone that's constantly coming over to you and hassling you in the office. You typically try to police it. You try to not just redirect it, but say, don't call me, stop coming over to me. For prioritization, your manager comes over and says, drop everything, do this. Software doesn't do that today. We expect that. We expect software to be able to prioritize certain activities. Predict is when your manager comes up to you, gives you workload, and says, I want you to do this. What do you say? I say, well, it's going to take a week. Software doesn't give us any answer today. It's like, I'll wait. You call into the software, and then you just wait. The thread just waits. And says, okay, how long should I wait? It depends on the timer. So, that's a typical approach. So with software, it can predict what's going to happen and whether it's available now. And of course, once you've got prediction, then you can start to provision, because you can look what's coming and then say whether you can actually do that. So when I come over to you and say, how long is this going to take? And then what do you say? Well, it's going to take 2 weeks. And I say, well, I want to know in 1 week. So what do you do? Go give half of this to this other guy. Or hold on to my heart people. So we do that today in our systems, but our software doesn't do that. And that's what we need the software to do. So the way to do this is feedback systems. Observe, make a judgment on it, or determine what's relevant, and then to react on that. So we need a feedback system built into the application itself. And now what really Java and some other language has to do today is to come out with probably a first-class, make it a first-class citizen in the JVM itself, that resource management, self-regulation is already built in. There is a feedback system in place. There is already a feedback system in place today, by the way. It's called the GC. Every time you do work, it stops your JVM. It says, I'm going to stop the world because you just allocated all of this memory and I'm going to slow down your system. So there is already kind of a feedback system and dynamics in your application today that's trying to throttle your behavior. And it's called the GC wall. As soon as you do too much, GC stops every thread and says, hold on, I'm cleaning the garbage. And then as soon as it's done that, it finishes. The problem is, we're not learning.
Also, if you like a web server, you probably configure how many maximum number of concurrent requests that you would process, right?
Yeah, but the problem is you're deciding that.
It's not that. Yeah, it should be dynamic. Yeah.
It should be dynamic. Yeah. Now, so the typical way to do that is called hill climb. Is that you start, because every system has a limit. Now, so every biological system, or every kind of adaptive system, always tries to find its limits. And then as soon as it gets close to those limits and sees that its behavior changes, it backs away. But you're always going to push it. It's like going to the gym. You will always try to use a bit heavier weight. And as soon as it comes crushing down in your chest, it's okay, not that time next time. That's why we have a spotter. Help! So we know our limits, but our software doesn't have that. Because it doesn't remember. Like, if you go into a car dealer today and you got bad service, and you made a complaint, then the next week that you went in, do you expect to have better service? Yeah, you expect them to have the great carpet. I remember him. Now, when software comes in, when software fails today, let's say a web request comes in for a user, and it's slow for that user, what's the probability that the next request will be faster for that user? Is it independent or not? The software doesn't understand it. It won't even see that other user. It will do the same thing that it always does. It doesn't alter its behavior. It doesn't say, hey, I gave you bad service. The next, I'm sorry about that. Well, I'll make sure you jump ahead of the queue this time to compensate. So the reason why software really fails, or why people complain about performance so much, is that if you notice, when people do something wrong and then immediately correct their behavior, or at least try to compensate for that, people tend to forget about it. But software today, if you go onto a web page and you click on one web page and you go to the next web page, and if that's slow and the next one's slow, then the software is slow. Everything is slow. But if you can make the next web page to be fast, guarantee that it's already there, then humans tend to forget that previous slowness. So the solution is to always make sure that you correct your bad behavior immediately, not later. And that's how to do it. Well, I'll get on to it later. So, if I have time. So the control system, typical control systems there's a controller looking at the process. There's always this kind of disturbance in the system itself. But looks at the process, allows it to work through, takes a reading from the sensor, and feeds it back into the control system. And then it decides what it should do. And we need those kind of mechanisms in the JVM itself, or in applications. And we have an example of that in our own code, is that we have an auto-tuner that he measures code and he looks at the meter readings from it, and the meter readings go into a monitor and then it goes into the controller, and the controller adjusts the threshold higher. So we can actually say that I want this method to always execute to be 120. And let's say the method is executing in all instrumented and all the methods it executes is 200, but the controller will keep raising the threshold until it gets to the right threshold. And the threshold is the kind of the code or the turn off threshold. I have an example here. So we have an auto tuner, and this is just making calls here. It's making 5, it's calling 5, 5 calls 4, calls 3, calls 2, calls 1. And if I just turn this on, the auto tuner. So if I run this with instrumentation, I'll just get the timer for it. It's got instrumentation, but there's no tuning in. So it takes 827 nanoseconds because it calls 5 methods each of those. Now, if I run it without any instrumentation itself, so if I just take off the instrumentation, this will generally execute 114. Okay, now I want the system not to be 800, I want it to be 114. So what I can turn on is the tuner and say, okay, enable the auto tuner and keep increasing, start the threshold at 1 microsecond and keep increasing until I make 120. I want that method, the top method, to be 120. It's 115 now, but I'm going to allow an overhead. So now with this, it's still going to measure it, but it's going to adapt to the goal. And there's one. Oh, sorry, I didn't actually know. I didn't even measure that was wrong. But that was too quick. I'm not going to cheat myself. So that's 121. And if I go to the file, you'll see that it measured, it was still instrumenting the methods. But it actually disabled the methods to get to that goal. So all control systems have kind of a goal mechanism where there's a controller looking for a goal. Now the goal could be less GC. So in terms of, people always saying, okay, great, that's great, you can do that. What about me? Well, what about if you had a server filter that said, I like my GC to be within 5% or 10% of my total time. Now, and it allowed more work to go through while it was meeting that threshold. But as soon as it started to go heavy GC, it started to throttle the workload. And that would be like, don't have so much concurrency, because clearly I'm breaching my requirements. So you can do this already today by thinking about the system in a more dynamic way to say, okay, I've got these constraints or goals I need to achieve, and how I control that is the concurrency of my system. How much resources I give, or how do I allow the consumption to happen. Now, so, to come back, how do you know the threshold or the threshold size? This is always a problem. People put in 10. Every time I see 10 or 100, oh God, why is it never like 92, 93? It's like 100. You know that someone just made a guess.
Should be 128.
Yeah, like you just like, that looked like you did some kind of test. It's like every test, a performance test starts with 1,000 users, and then it goes to 10,000 users or something. Now, when you have, so if you talk about a system that's suffering, or, we always talk with JVMs, it's always about these, the big problems are the workload. There's no control mechanism in place today, so we tend to suffer big GC, like there's products like Result has been here before, and they're really selling GC systems, GC management. And that's because that's our big problem in a lot of these JVMs, is that simply there's no mechanism to control the workload, it just keeps accepting. As it keeps directing, if your web server keeps directing traffic to Tomcat or whatever your web container is, you can keep executing the code. You won't say, oh, hold on, I'll wait a bit because I'm too busy doing the other stuff. So with the problem is that as the requests go up, we get higher throughput, eventually we hit a limit and we start to go degrade. The system starts to degrade itself. Now with adaptive control, what the adaptive system does, it allows the throughput to grow, but it's monitoring with the feedback system, it's monitoring the throughput or the rate or the response time of the request. And as soon as it starts to change the other direction, it reduces the traffic or pauses the growth of the concurrent. We have these are still concurrent requests, but the actual real concurrency has been paused because it determines where the limit is. Because we want this flat line, we want to stay at the maximum. We want to go straight along that line. We don't want to dip, but we'll keep going up until we start to get to that dip. So here's a system, hill climbing, typically start with one thread. And this is on a system that's an application that's running, adds 2 threads, moves up. These are not threads, these are actual the throughput that's increasing. And as it increases, this is the hill climbing, it's allowed more threads in to do more work. And then occasionally it increases the workload, but the throughput drops. Now you might think actually the throughput, I've actually increased it. What's happened is the system increased the amount of concurrency allowed, but the overall throughput dropped. And what it then did, it adapted back, it brought down the throughput, and then it brought down the concurrency, and the throughput went back. So that's a typical kind of mechanism in an adaptive system called hill climbing. It's called local searching, where you search for an optimization level, and you always hit the limit because you need to know when to stop. So you're always going to have a part where you hit it, where you start to degrade, but as soon as you see that degrade in performance, then you step back and say, I'll do that again. And that's what the software does there. So, this is it over time. If you look at this, this is the metrics, measurements, and this is the throughput. So initially you start with 20, and every time the system tried to probe a higher limit, it went down to 10,000, and then it went back up again. And occasionally it goes, you see the drop, you probably think the drop is a concurrency, but that's an increase in the concurrency, but the throughput drop as a result of the increase in the concurrency. And that could be because you're allowing more faster allocation of objects, or there's more contention on a lock. I'll give you an example. So if we go back to, let's say I'm going to put in some code here. I'm just going to copy this code in. Okay, so there's a lock contention there, yeah? You'll see here that I'm restricting it, and I'm going to have this do 20 threads. I'm going to run this. I'm going to run it from the instrumentation. So I'm just going to run it and make sure I do the right one. I'll come back to this one. I'll come back to it. It's just I have to get the numbers a bit worse on this one. I'll come back to that anyway at the end. So the system, because I'm worried about I won't get through all this stuff. Well, all of these systems have basically what we call system dynamics. So system dynamics is you have inflows and you have outflows and you have stock or resource. And so like we talked about with population systems where you have a population growth. You increase the birth, the births, people are born, increases the population. Of course, there's a feedback system. The more births you have, the more population the growth is. Of course, what we want is a balancing loop, and death is the typical way of controlling the population before it runs out of the system. So what we want is to take these kind of dynamics and to put this into our application, that it has these reinforcing loops. Sometimes we want to reinforce a loop because we want to grow. That could be in the hill climbing. If we are successful in getting more throughput, we want to increase the throughput further. But of course, as soon as we hit a balance, then we hit a limit, we want some kind of balancing loop that adjusts itself, says, okay, I'm suffering, so now I'm going to reduce this stuff. So how we can manage systems is by taking a resource and controlling the ability to consume that resource. Now we have that in Java today, it's called a semaphore. So in semaphores, you have a number of paraments. That's a resource. And so you can control, so in your concurrency system as requests are coming in, let's say, so you have a servant request, and you're allowing the request to go through. Now initially you might have a semaphore, you'll have a semaphore, and every time a request comes in, it tries to get a parent. Yeah? And so you initially start with maybe one parent, and you look at, and you run that, it goes through, you're running that for a few seconds, and there's no GC, then you say, let's increase the parents. So you release another object, another count into the semaphore, and it loads two threads that you want to further. Because every time a thread comes in to do its operation, it requires a parent, does the work, releases the parent. So what your system can then do is take these paraments and increase this stock. And every time you go in to do work, you have to consume the semaphore or the parent and then to release it back into the system, which is the kind of feedback balancing mechanism. Now, of course, as we keep growing that, as the system sees that there's no impact to the response time or the stability of the system. But as soon as it starts to see response time slow, it will not release the parent. Now one way is it won't release the parent, or the other way is that because it gets slower, the parent doesn't come back to the system. So there's already a kind of a balancing mechanism in. If I start to increase the number of paraments, and something takes a parent and runs, and it gets slower because I've put too much work on the system, then the parent's going to be held longer, which means other threads can come in and get it consumed as quick. So there is a way to be able to balance these systems, but we have to control all the software via these kind of objects that represent parent stocks. And this is what we view as an application software. We'll take the application software today, and then the system dynamics, which is these kind of resources that we're going to control, artificial, and then we'll merge them at runtime into the application and self-regulate the software. So what does that look like? So I've got an application here. Just take this simple app. It's doing an incremental account. Yeah? Now if I run this app just on its own, you can see that it's doing 836 requests a second. Yeah? Okay? 800 something. Now I can control the system by saying I want a QoS. Typical QoS is just a quality service. And I'm going to define a service called C. The C is just code, just think of it. And there's a code called app call, which is in here. And every time app calls, he has to go to a resource. And I have to find a resource called T. And what I'm going to do with T is, I'm going to make T a capacity. I'm going to give it a capacity. And I'm going to fill it up to 20 every 100 microseconds, or milliseconds. So every 100 milliseconds, I'm going to put 20 in the bucket. And then, of course, the thread's going to come along and consume this. Well, I can use that the way to control the system. So if I turn this on now, run it, so it's going to, every time it comes in here, it's going to go to a resource and say, I want a paramount. And there's going to be a limit of 20 paramouts per 100. Now, we're not renewable. It's a non-renewable resources. In system dynamics, we have renewable and non-renewable. This is a non-renewable. It's typically you take something from the ground and doesn't put it back in. If I run that, okay, so that was the. Now if I run it with the QoS enabled, QoS. Now I'm not changing the code, so this is still app. You can see that it's 200. This code has not changed, but I've changed the behavior. So if I say now, let's give only 2 credits, 2 in the limit, 2 every 100. I'm changing the software, the behavior of the software is now controlled. So the software has not changed the code, but I've now taken this model of a system that says there's a resource and it's replenished every 100 milliseconds. and I put 2, the replenishment is 2. If I put in another number, if I put in higher, like, what did I have before? Was it 20? If I put in 50, I increase the system. So this is the kind of control that we need to manage applications, is that dashboards should not have red and green circles. They should have knobs that say, release resources, pull back resources. That's the way we manage the system. And of course, a system could learn over time what works and what doesn't work, because we don't.
So here we can just slow down the system as the calls originate from the system, but like in case you're handling web requests,
Yeah.
where we just slow down things,
Yes.
we'll have the requests queuing up and the queue will get longer and longer, and
Yes.
you need another second.
Yeah, but you might think that it gets longer and longer, but actually, in fact, I might get quicker and quicker because I'm not taxing the system, and the system can run quicker. Because we've already seen with adaptive system, we hit a limit and then we drop. And we start to
have more requests per second, but even that's being completely swamped. So the system, okay.
yeah, but if I'm completely small, then I want to protect the system. What would you rather? The JVM disappearing? Or
Well, the second level, well, first we do the throttling, but at one point we also need to start rejecting requests, right?
oh yeah, okay, so that's where signals comes in. Yeah. And I don't know if but that's where we have to indicate. So the problem today is, one of the biggest problems we have with software, another one is that when I go over to you and you give me work back, like let's say you're a hash map and I say get, and I give you a key, you go get it, and you come back with a response. You give me the result. Now when your manager goes to you and says, did you finish that work? And you say, here it is. What do you also say to him? Well, typically a manager, a good manager, will say, how did it go? You know, what slowed you down? Is there ways we can improve the efficiency? Or why were you slower than normal? And you'll probably have some reasons for that. Now, software today just says, here's the value. I don't know what I did. I just got the value. Honestly, because software, what it does is one method calls the other method. He says, I don't know what you're doing, but I'm calling you. And then he says, well, I'm calling the next guy. And software today does not understand itself. Now, so a hash map, let's say you're a hash map, and you went in, I give you a key, and that key hit a table, a linked list, and that linked list had 1,000 or 1,000,000 elements in it. And so you scanned along the whole key, and then you found it at the end. Now, if you were software, or human software, you would come back and say, I've got your value for the key that you gave me, but I have to go to the whole of the end of that queue, or the end of that linked list. Because your collisions are cracked. Your hash code is cracked. Don't give that to me again. Change the hash code function. So, what software should do then is not just return results, should return signals. Now, if HashMap was a good class, now I'm not asking for another object. I think we have to come up with what a signal is. Don't think of it as a return value, but there must be a way for the software after a method is executed to say, what happened? And he can tell you, I've got your work because you would give me the work, and then you would give me the reason why you were late and delayed. And he would say that I did a linked list scan and I hit 1,000 elements in that scan. So HashMap, and remember that problem we had recently with HashMap attack, because people had engineered a hash code or engineered a request that hit the same hash entry. Is that the software would see that happen, and then you would understand the causes of it, and maybe try to adjust. You probably change the system itself. Adaptation will happen is, let's change the hash code. So what we need is the software to send a signal.
The hash map example is actually a good one, right? Because you talked about you want to be, you can easily say the code is, we want to, by default, expect a certain maximum collision rate. And so that kind of stuff that's pretty general. You'd like to encapsulate this with like annotations in your code, right? But here, so you're using the standoff config file.
Yeah, but it's just a mechanism it's a mechanism that keeps the code separate to the dynamics. See, operations people, the problem with developers is that when you're writing your code today, that first of all, when you look at a method in your editor, you can't tell me the cost of that method.
Oh, but some of you can. It's a matter of algorithm design versus operate. This is this whole sysop or whatever. Yeah. Things that are part of algorithm design. This is the kind of thing that's actually been traditionally a problem, right? Is that you actually design an algorithm, you have parameters that you can say, not based on its deployment. you don't have to, it isn't an aspect of, in general, at least by default, a matter of how to apply the system and say, oh, no, this algorithm expects to be able to do this. And in fact, you have to set X, Y, and Z parameters to get it right.
Yeah.
And the only way to get it is through measurement. And there may be thousands of these in any particular system. And you wouldn't want to have to tune that for every, nobody should have to tune that if you can already design in the algorithm. Okay, here are identical parameters, here are the features that you should do when you're metering the system, when you're doing profiling, set these parameters for each case.
Yeah, well, they will always, the problem is if the code changes, if some power, if there's increasing consumption of resource capabilities because of the code is parallel, that someone has said I can scan to many cores on the system. So you can never, at development time, I think the developers have to hint at the resources or hint at what signals are. Developers have to put into the system signals. So I believe that if the person that's creating the hash map should put a signal in that says the signal, and a signal has a name and a strength. So the signal here would be link scan or linked list scan, and the strength would be the number. It doesn't have to be, it doesn't matter what the number it is. What we need is a kind of a token, a tag, and a value, a strength of a signal. And then we can apply normal signal processing systems, technologies, where we look over time at our response. Because we can't measure hash map get because it's just too quick for most of the cases. But let's say you have an overall, every now and again you have an application response request that's slow. What you can do is if you look at all the signals generated by the components in that who signal something when it's unusual behavior. It's not exceptional, but it indicates that the cost is beyond the normal algorithm cost. Yeah? And then it says, okay, I'm in the worst case. Now, what we can do over time is figure out every time we have a request that deviates at the high level. We look at his clock time, which we can measure because that doesn't cost too much. And then we look at the signal set. And we match signal sets to when the request exceeds the threshold, the typical signal set looks like this, and there's a common match. And the signals, there's one or two signals that always seem to be present in each signal set, and they have this particular strength. Now once you have that, then you can figure which component is the one that's driving the cost or driving this deviation behavior. So we want to figure out who's causing the deviation in software, but we can't measure it because it's just too fine-grained. We need a signal. Now, and of course the software itself doesn't have to understand that link scan, what it means. It just needs to know that every time that this goes wrong, link scan comes up. Now, of course, then the developer later on figures out that that's the problem. But for the software, it needs to be able to filter all of the signals down to the core signals which drive the measurement of the behavior. So we have performance being the behavior measured, but the signal sets indicating deviation.
Let me give you an example where, so besides map, for example, places where there's these tens, etc., and besides threads, there's a string builder, right?
Yeah.
And so, how many people bother to supply an initial size for?
Yeah, well, resize.
But this is something that could be tuned, but you're not going to do it. It's not operational. This should have to be something.
No, but you shouldn't do it unless it becomes important. Say, okay, yeah, so because all of these signals will be generated, but eventually the ones that are most important to the application will rise up to the top. So if you take string builder as an example, the costly part of the string builder is the resizing of the arrays.
Right.
So a strength there, the signal will be resize. And we might have two types of signals, resize count, the number of times that we did resize, and then the other one would be the resize size itself, which would be, because it might not be the number of times we resize, but the actual space we keep resizing to. So we have two signals generated. So let's say when a request comes in, and occasionally it's slow, or like even let's say a database, you go and read, instead of reading 100 records, you read 1,000 records, or read 10,000 records. The signal there would be result set count, and the strength would be the number of records. So what we need with this system, it's kind of like counters. But they, you know, it could also be like in a method where we have, an if else, and one part is cheap because we have the fast path. You know, the hotspot has fast paths and slow paths. And what we need to know is every time we do the slow path. And so we can just have a signal there. Now, over time, we keep measuring the system at a higher level, but we'll see the signal sets and we'll correlate them. But it's still causality because we know this request generated this signal set. And then we'll look for which signals are important. Now, string builder might be always generating a signal, but it won't be as strong in these requests. So the relevance will come when we correlate it to measurement of deviation in behavior. Then we can say that this signal set of this label, whatever it means, because the software won't know it, is always the driver to this change in behavior. Machine learning.
Yeah.
Because machines don't learn about themselves.
Why would the signal generation be cheaper than the cost of the measurement?
Yeah, because that's what we have to make cheaper. So that's what Java needs today, is to make thread counters that are cheap. That I can put in a line of code, let's say I'm in a for loop or if I go in if else, that I can say I want to annotate this line or some kind of marker or a label on the line and say signal. And by default the signal will be 1. So I can say signal based on a number or something that's in the code, or signal will be every time like a trap. Every time you go over this line, signal. Now, whether something is listening to that is something else. That's an issue. Is that the signal will stay there. It will go through boundaries, which are called methods, scopes. And what you can do is you can use a complex event processing where you generate the signal set lower, and then people have a scope, like a method, and he takes that signal set and turns it into a higher level signal set. Because you don't want the signal for hash map to surface upwards. So what happens is that if you take a data grid, you want the cache miss and hit the miss. Now every time the cache does some kind of behavior or it uses hash map, it will take that signal and turn it into a signal that's more meaningful, higher level. And it's a bit like exceptions, where you catch an exception and you throw a different type of exception that has more meaning to your service.
Well, I guess what I'm talking about is, so we have quite a few of these classes that have initialization parameters.
Yeah.
We need, how do we, each constructor call needs to have these tuned parameters.
Yes.
How are we going to get them all in there, right? So there's thousands and thousands of constructor uses for each of these classes, string builder, maps, caches. So they are all going to need, and of course you can't distribute them all right at the same time, right? So you're going to have a budget that's going to go across, swoop through the system and adjust all these parameters. But how do we get the individual parameter values set into the code to all those constructor calls?
Most system signals are bidirectional. So the brain itself, so signals will come up and we can send signals down. The signal is, I go over to him and say, I want this done today.
But I mean the code.
So the problem with hash map today is you have one hash map by one request. Let's say you have request type A and request type B. Really every request is going to use a hash map. But the usage of it will be different.
Well, that's different call locations. So each call,
it depends on the request. So it will depend on the request. Like this request comes in, and then typically, let's say for every time this request does, you add 10 items into the map. Now on this request, it adds 1,000 items into the map on average. So the next time you come in, you look at your signal set, and you say, what did I last time add in? And so you take your request and you have a signal profile. And you say, this signal set looks like this. And you pass the signal set to the next guy underneath. Because, by the way, signals are always scoped and boundaries. So you say this, every time I call you, I get this signature. Now, because this is map, a map says, hey, everybody's calling me. Can you tell me who you are? So how do I tell him who I am? I'm request A. So what I don't want to tell him, he doesn't care about what request I am. He just needs to know is, what's your typical usage? What do you need me to do for you? So I say, well, every time I call you, this is what you do for me. Here's the signal that you previously gave me. Use that to drive your behavior. So when I construct a map today, the map will say, you don't provide me parameters, provide me the signals that I previously generated for you. Now, so my responsibility then will be to distinguish myself from this guy, from that guy. So that will be at the request level. So every time I want a deviation on the hash map to be tailored to my needs, I track the signal set and I store it somewhere. And then every time I go to the hash map, like, or whatever, my next component, I give him the signal set and say, this is what your behavior is, use that. And he takes the signal set, adapts himself, runs the code, generates a new signal set that might learn from that signal set, and then gives me that signal set back. And then what happens here is we get an optimization. So maybe the first time he resized so many times and uses that to gauge the way he should size himself. But he gets it wrong. It's an estimate. The next time I give him another signal set and he gets it better. So if we think about concurrency, it's a bit like hill climbing. We use those signals and we feed back into the component. Now every component that calls someone else has to track the signals. So it's like a supplier.
I understand the question. We talked about the method, right? We said this a bunch of times. It's the same process. My question was, if I wanted to use this instrumentation technology, take JSON and I want to for every single, for example, all these low-level classes that are wasting, that could be tuned for resources, to choose for each constructor site, for every builder call, map constructor.
I know how the solution for you today. I'm not going to. No, this is the vision. This is what we.
This is what would make this. Because all the code needs to be adaptable and special.
Yeah.
Because this is you start out talking about how Hotspot does this, and if you're going up one level, that's really the next level up. Is not you're jumping way up the system about.
Well, I'm putting a mechanism in to make this adaptation happen, but I need the signals to be put in by the developers. Because I'm creating a mechanism, a machine system, that can learn based on signals, even though it doesn't understand the application. So I'm creating a grammar for the system to learn, but you need to generate the symbol set.
Right, this is why I was talking about this issue, start on this road, talking about the configs files, right? Because the way programmers today like to provide metadata about code as implementations rather than config files, which are considered pretty equal these days, right?
Yeah.
So, I mean, sysop guys like because they work on text files, and so you want to think about external things, but if you want to think that are tied into the structure of the code, we're going to be looking for annotations, not some separate file to maintain and send line of code. This is to map all these signals to the code.
Everybody needs a node. Everybody needs controls. There is always have to override. It's a bit like, a complex system is like a trading system. And you need every now and again to inject money into it, just to kickstart some process. So there has its own dynamics, but occasionally you need to influence a system to direct it a certain way. So, and systems, by the way, need this. It's very good for resilient systems to be given shocks and to be given kind of changes in the system. Because systems can go into a dead zone where they don't adapt. Yeah? And sometimes you need an event to happen to cause adaptation, like a meteorite hitting the Earth. You need some big event to kickstart a new cycle because you get into a dead zone. Honestly, seriously. So well, I'm just trying to get everybody to imagine this, and then hopefully this will eventually get into some kind of language, or maybe Java. But I believe if we stop relying, if we start thinking that the software can do it, the JVM itself can do this, I believe we have to get to this. Okay. Well, I'm nearly getting finished here. This is probably the last 2 slides I have. I just wanted to leave that part of that I wanted to come back to is like performance optimization is predictive. Now I already showed you that with the signal set we can influence the behavior later on because self-regulation systems need kind of a current configuration. But that configuration has to be dynamic, so we need to collect the configuration and then pass the configuration back in. By the way, an example of this would be the hotspot. You know the hotspot today, where every time it runs your code and it runs your code again, it learns all over again. And I do believe that JRocket at one stage had a capability to export the configuration and to read that configuration in the second run and use that to drive its optimization. So somewhere you have to post something and push it back into the system. So that's another example of where they take a signal set, which would be the frequency of all the methods that were profiled and whether they were optimized or not. And then the next time the instantiation of the JVM, you push that back into the system. So that's another Okay, well, big problem we have at the moment is we have thousands of cores, or we're going to have hundreds of thousands of cores, and we have to get them to do some stuff. But the problem is they're not getting genuinely faster. They're getting smarter. There are still some gains, but they're not probably. The throughput is increasing much better, but the overall efficiency is not. So we've got cores, and we want to increase. We want to use those cores. So, but the problem is that we have jobs that if we start to break them up, we have 1,000 cores, and we take a request coming in and say, how can I partition this job up? Now, I could slice it into 1,000 parts. Now, it'll take me time slicing it up into 1,000 parts, and then I have to push them, schedule them to be executed in all the cores. And then they have to be all merged back in together, and then coordinate that and get the data. You know, the kind of mapping we use, the typical kind of mechanism like that, but more for core processing. The problem is, I have a limit. Even with, we all know Amdahl's law, you know, typically you'll only get 20 times speed up. So, and our users are constantly asking for fast and faster response time. You know, when I started in this industry, it used to be like 5 seconds was fast on the web. And, you know, nowadays people are saying 200 milliseconds is slow. We've gone from 5 seconds to 200 milliseconds, and they're saying like it's going down to 100 milliseconds to even instant, you know, like at least to our eyes. So how do we make it go faster? Because the latency is there. We can't beat some systems. So the way to do it is to predict already. The way to make a system faster is not to do it in the first place, is not to do the work. I mean, we could break up the work and get everybody here to do it, but it just takes too much coordination. And then I'm still waiting for all you to finish it, and then I have to give it back to the other person. Now, what happens if my manager came over to me and says, I need you to do that, and I go, I've got it done. Now, there are cases where we have those kind of, where we already know our manager is going to ask us to do something, and we already do it. You know, it's like in your design, you already factored in a requirement that no one had given to you, but you did it because you knew it was coming.
But then you shouldn't say that you've done it.
No. Well, of course, in this we're being measured on that. So if we want to make software go faster, we have to do the work, but do the work before it arrives. Then we don't have to do the work. The work is not done. It's already done. So as I said, you know, the way to make the system faster is not to do the work, but not to do the work in the time frame of the user. So with systems, what we're going to have is more prediction, where we're going to predict what's coming and already have it loaded. And then we already do this a lot with preloading of data into caches, maybe preloading pages in the background, all that. So what's going to happen more in all of this core development is that once we get to these systems where it's more adaptive, it's going to predict its changes. Because that's what, by the way, you know, systems do themselves. Complex adaptive systems use the signals and then they adapt. And adaptation tends to be more about what's predicting what's coming next. You know, of course, there can be disturbances which cause it to happen, but sometimes adaptation could be, there's a new prey or a new predator in my environment. I'm going to get out of here. You know, because I'm going to be S. So there are systems where they can already see the signals and use that to predict and change their behavior already prior to being computed. So I don't know if you know this sport called curling. Curling is you get this kind of stone and you throw it along the ground, and it's ice rink and it flows, you know. And there's two people in front with a sweeping brush. And then what they're doing is they're getting rid of friction, because we know friction slows velocity. You know, well, increases the velocity, we get a standstill. So if we want to increase or keep our velocity, improve the speed, or keep it constant, then we have to eliminate friction. And friction is loading, waiting, delay. So what these people do is they have these other two guys running along ahead, and they're sweeping the ice to make it smooth. So when the stone gets to that surface point, the surface is smooth and it flows. So if we want our software to get faster, we need to already eliminate those friction points in the system and have the data there already before the request comes in. As the request comes in, it's there. So what we have all of those cores doing is not doing processing about what's happening now, it's doing processing about predicting. And the great thing is, if it gets it wrong, it didn't cost us anything because we weren't waiting anyway. Because the cores were there. Of course, we are increasing our power consumption, so if we're going to be green friendly, it's probably not so good. But predicting is not really a problem because we're relying on it. I mean, if it's there, it's there. If it's not there, then we incur a hit.
It's okay to predict as long as you're not changing state, right? And it's not okay to predict.
No, yeah.
So how do you at the
Well,
instrumentation panel know that it's safe to do a prediction? I mean, that's why you can
That
do
will be
that.
application specific.
Also, the application designer has to know.
Yes. I'm just saying this, because a lot of this is not the JVM. Well, the JVM is like pipeline processing. I'm saying is that we're going to have to apply those kind of techniques at the application level. And those kind of techniques will be more application like get the data for the user. If the user came to this page and 9 times out of 10 he always hits on the settings page, then you already have the data for the settings logic. And of course we're getting to the stage where previously we didn't do this because we always wanted that we get the current data. Everybody is don't ever load stale data. But now where we have more this kind of eventual consistency, people are saying, we'll just load the data anyway. Preload it. So we're already moving to more of the softer systems in terms of the isolation and the transaction concurrency, that we might as well just kind of preload it and have it there.
How is that going to be done with an automated tool? Isn't the whole point of this that there would be an automated tool?
No, some of this will have to be.
This is just hand-coded, like just a smart.
But we need kind of a mechanism in place that allows the developers to hook in this to hook into a system that offers those capabilities, a framework for this. So, like it's like this adaptive mechanism. We need a runtime that makes adaptation first class in the language or in its runtime. And the same with this kind of prediction. We need software to have this predictive capabilities, and all you have to feed it is parameters, and it generates something else or performs an action. What we really want as a system is not to predict. The system only needs is to predict what the action should be, but we will put the action there. So we need to still do the action, but we need to give it a kind of the parameters to use for the prediction to generate the action, to map it to an action, but the actual action will be the application itself. So the prediction system, the system that drives this, will not have to know that. It just needs a bit like the signal set. It just needs to know a symbol and needs to map it to an action and then just trigger that action with the symbol set.
The risk that you're going to create, we already know that concurrency is very complicated. You're creating a new dimension of predictive behavior, then you can create bugs that only work when you run it in predictive mode. And to figure that out,
But we have to the hospital today. We have to the hospital today.
It's already done in CPU.
It's done.
Yeah, but it's safe in the CPU because the CPU knows the bounded space. The problem, the CPU won't write anything persistent to RAM on spec. It's going to do the 2 branches and kill the branch that didn't need it. Because it's not going to write new values into its database, which then is like, oh, well,
This is probably functional programming solves some of these
right. But
I do believe that's
also
part of
trade-offs,
it,
'cause you're
where that will
replacing-
make a lot of this easy.
If you have an external system like a database, if you put load on the database, at the application level, you have these problems, right? I mean, I could be calling the database on spec. Well, it turns out now my system is running like a dog because I'm predictably calling my system.
But if you penalize bad behavior, the system will learn over time. So the problem with prediction systems is you have to penalize them for getting it wrong slightly. Penalize them so then they become adaptive themselves. So the predicting, what I'm saying is all of these systems become adaptive in some kind of frame of reference.
But it's not clear that it comes to an equilibrium. I mean, that's...
No, but they never, no complex adaptive system has that equilibrium point, at least for a period of time.
But I mean, it might come to a negative... I mean,
Oh, yeah, but it will. It fluctuates. But
it might not fluctuate. It might be that...
You already have it, like,
Yes,
the cache, it's in the cache, it's not in the cache.
You could perturb into the wrong direction. You could make your system...
Yes, but the system,
adapt
if it
to
learns
this.
enough, it should adjust back.
But that's not... You can't be sure of that. I mean, it may be that it...
I can't be sure that I can put algorithms in that can stabilize a system. You can't put algorithms in, apply algorithms that will stabilize it.
You can make the system smart enough so that it measures itself and if it finds out that it's a negative effect, it just turns itself off.
Yes, but that's something that works on simple linear systems. And the point is that this
Well,
is
I
not...
know, yeah, but-
You're not adapting a linear system.
I know, but there's no, but okay, I know that. I know there's no equation for it. But I'm saying is that as long as people always say to me, prediction. I always say to people, if you can react to stimulus or to signal as quick as I can observe it, then it looks like you predicted it. So if you see your manager coming over to you, towards you, and you know what he's going to ask, that's a signal. You see him coming, and you write down already what he needs, and by the time he comes, you have it. It looks like you predicted it, but you didn't predict it, because you recognized it already, and you generated the response. So I'm saying there's a lot of adaptive systems. They can be wrong, but as long as they immediately, and that's important, that they have a very quick feedback loop to change, then it looks like they're predictive.
Yeah, but I don't think it's as simple as that. I mean, say for instance,
No, it's not simple.
well, let's say for example, right, you do the predictive call, which goes to the database, which causes the database to move out of cache the data that it really needed and put the wrong data in cache. Now the other guy comes in, makes the call that he's waiting for, and now it's slower because the data's out of cache. You penalize the wrong guy. You penalize the one.
We do that with GC today. We already penalize it.
But I'm just saying that there's no guarantee that. I mean, there's a whole theoretical question as to whether you may actually optimize to a worse.
Yeah, there's always a trashing. Yeah.
But you should get notified about it, though, right? I mean, as part
but
of
that's
but
why,
the wrong
okay,
guy is
but
getting
that's
the
why.
signal.
But that's why the system
You're going to charge the
occasionally.
wrong guy because it's charging the guy to do the right work. As if because he's slow because the cache is out of date now, because of the predictive piece coming in, and it's because of the interaction. It's right.
Yeah.
It's
Okay. There's a local. Okay. I think what you're talking about a local maximum and a global maximum. So you're talking about global and local. Yeah, but that's okay. So how do you solve the global? So we have a valve. We have an evolve system. I don't know how time is. We have a valve. Okay, yeah. We have a valve system. But anyway, what you do is an adaptive system. You break down the system. So every now and again it learns and it says this is the optimal level. And then what you do is you have a reset. And the reset relearns over again, because you always have to do a reset because you might have learned just to hit the top particular max. So there's always a reset where, and we do have it in our valve itself. Okay, I just want to show you. So on the signals, I just wanted to show this one. I've never done this. Okay, I should never have the questions. But basically, so what we have is, we have these signals that will move up. So these circles are basically scopes, code blocks, methods, nodes. And this is like this method calling this method, this calling method. And signals will move up. Now, every method will have a boundary. And what we'll do externally is to determine, and this will be in the configuration, whether the signal will permeate, or like in a cell, if you think of biology like cells, where the protein will be able to move across the boundary of the membrane. So what we need is some signals to be dampened or to be contained because they're not useful to something above. But for other signals to move up to the caller, and then maybe for him to take those signals and turn them into different types of signals that will go to the other caller that are more relevant. So we have exceptions today, but we need exceptions. The problem is they're exceptional. And what we really need is a way that's less intrusive to the system. So if we did is, all we did is generate a signal set and flag the strength. Now what I have to do then before I do a method is I go to the signal system and say, tell me for this thread what's its current signal set, the current numbers. And then as I come out of the method, it's a bit like a meter, I ask for the new signal set. And then I take one away from the other, and whatever's changed is the new signal set. It's the signal set, the delta, what's fired. So let's say the signal before I went in this signal has been fired 10 times, or it has a strength of 10. And then I come out and it has a strength of 20. Then I know the signal had 10 units was incremented. And I go in that scope, and I take that 10 and say that's a signal of 10. Now I can turn that signal into something else and generate another signal upwards. And this will be, now I'm not generating, I'm not firing it up, I'm putting it into my scope. Now the guy that called me, if he's interested in listening to my signals, he will do a save point, what we call it a save point. He goes signal set save point, and then he goes compare, and you generate the new set. And then he takes that set, and if he's interested, he might consume some of the signal himself, or he might forward the signal upwards. But what's going to be useful about this is no one's going to have to change any of the Java classes, because we're not going to say that every Java result object has to be a pair object or something. What we're just going to have is that every signal is at a thread level. The signals are at a thread level, and they will be scoped. And so depending on the scope you're in within the thread, so think of it as a stack. And then every signal goes into the current stack scope, and then they can go the scopes if they're propagated by the method or by the administrator. So I reckon that administrators will over time will use complex event processing to define patterns or rules for taking signals and turning them into new signals which will go up. And those signals will be maintained and then pushed back down, and they're used to drive the system. Because the reason why we need to go up, because the context is up there, and the context is what drives my behavior. So for me to understand that I need to act, like it's when someone rings you, what do? Who is it? Because we need to know who the person is, and if, depending on the particular customer, you change the behavior, don't you? We all tend to adapt to the environment and to the person that's engaging with us. Now we don't understand who the guy is above us. Yeah? So, but if he passes in a signature, which would be the signal set, then we know, because like when someone rings me, I always look at his case, what's that case look like? Oh shit, it's that person. So that's me already recalling my previous experience with this guy. So we need software to have this capability to recall, to be able to still operate like William now, but to operate differently, slightly different in terms of my environment and the guy that's calling him and the context he passes in.
All right. I guess we'll save the questions for the beers. Thank you, William.